So if we start with the limit in a formal way, we can say if the values of fx, that means the function value of fx, that can be made as close as we like to L by taking values of x sufficiently close to a but not equal to a. That means we need to approach the function value to some limiting value L, capital L, by sufficiently close to a value a, which is the value of x. That means x is very much closer to the value of a, but not exactly equal to a. This is called the limiting value or limit of the function at a point x equal to a. So limit has two parts. One is the left hand limit, another one is the right hand limit. So whenever we check the existence of limit at a point, we need to check the existence of limit from both directions. That means limit should exist from the left hand side as well as from the right hand side approaching towards the point. If both the limiting values are same, only then we say limit exists at that particular point. Well, to have a better understanding of the concept of limit, you can follow the table 1.1.1 as well as the figure given below the table. As you can say, limit does not exist at a point x equal to 1, which is incorrect. You can say the function is not defined at x equal to 1, but still limit exists at that particular point. Function value does not exist, that is true, but limit does exist at that point. If we sketch the curve x minus 1 divided by square root of x minus 1, then the curve takes this form, the blue colored curve. This is the function curve. And we have a breakpoint or a discontinuity at x equal to 1. But still, we can see if we move closer to 1 from the left hand direction, the function value approaches towards 2. As well as if we approach towards 1 from the right hand side, the function value approaches to 2 from the upper hand side. Okay, that's why limit does exist at the point x equal to 1. Okay, and from the numerical values we can confirm this point. If we take x sufficiently close to 1, but from the left hand side. From the left hand side means from the lower value of 1. This is called from the left hand side. So if we take x close to 1 but less than 1, which is 0.99999, the function value becomes 1.99995. So this is the limiting value, not actually the function value. Again, if we move from the right hand side towards 1, then the value that we should take as an input should be little greater than the value 1. So we can see the value is 1.000001 and the function value is little greater than 2. So from both directions, we can see the limiting value is nearing to 2. Not exactly 2, but very close to 2. That's why we say limit exists at x equal to 1 and the limiting value is 2. Okay. So there are several ways to calculate the limit of a function at a particular point. The following example, you can also observe limit is existing at x equal to or x approaches to 0. Sin x by x, this is a quotient function where limit does exist at x equal to 0. But you can say limit is existing at x equal to 0, but function is not existing at that point. That means the function is not defined at that point. Because if we put x equal to 0, then it becomes sine 0 by 0, which is an indeterminate form. অনির্ণেয় আকার, that is 0 by 0 form, which is not permittable. So function value is not existing, but still we can see limit is existing at that point. All right, so you can take several examples from the textbook. Next, we are moving towards one-sided limit. Since existing limit at a point means limit should exist from both sides, but in some cases or in particular cases, we can consider one-sided limit. For example, if it is said limit is existing at a particular point, that indirectly means two-sided limit does exist. Okay, so if someone says limit is existing at a particular point, that indirectly means two-sided limit is existing. But if you mention one-sided limit, then you have to particularly say whether limit is existing from the left-hand side or limit is existing from the right-hand side. For example, if we consider this function absolute value of x by x, and we split the domain into two parts, since 0 is not included in the domain, so our entire domain is split into two parts. One is greater than x greater than 0, that means from 0 up to plus infinity. Another part is from minus infinity to 0 open. And it's a piecewise function, piecewisely defined function. The function value is +1 if we take x greater than 0, and the function value is -1 or -1 if we take x less than 0. And the function curves are drawn in the following figure, where we can see at x equal to 0, there is a hole. That means function is not defined at x equal to 0. That's why we see there is a hole in the positive y direction and there is another hole in the negative y direction. But if we take x greater than 0, then the function value is always 1. That means it's a constant function, so it should be a straight line parallel to x-axis and 1 unit in the upward direction. And the remaining part of the piecewise function gives a function value which is -1 if we take x less than 0. That means for any negative value of x, function value is always -1. That means this is also a straight line parallel to x-axis, 1 unit in the downward direction. That means if we take the limiting value from the left-hand side of from the left-hand side of 0, what should be the limiting value? If we take the limit from the left-hand side of 0, what should be the limiting value? Can someone tell me what is the limiting value of the function if we take the limit from the left-hand side of 0? Can someone tell me what is the limiting value of the function if I take the limit from the left-hand side of 0?
-1.
-1. Yes, you can answer the question directly from the graph. So we are moving towards 0 from the left hand side. So in the left hand side of 0, the function value is always -1. So you can say the limiting value is -1. But if we approach to 0 from the right hand side, then the function value is always +1. That means the limiting value of the function if x approaches to 0 from the right hand side is +1. So this part is known as right hand limit, and this part is known as left hand limit. And both the limits are different. So actually limit is not existing at x equal to 0. If we see, if we observe both the, if we observe both the limiting values are same, only then we say limit does exist at that point. Otherwise, we can only say limit is existing from either ends, not from the both ends. Okay. Therefore, one-sided limit can be defined in the following manner given by equation 14 and 15. Equation 14 says the limiting value of the function f if we approach to a from the right hand side, and if its left hand limit exists, then we say the limiting value of f of x equal to L if we approach to a from the left hand side. Okay. So 14 and 15 respectively representing right hand limit and left hand limit of the function if we take the limit about the value x equal to a. All right. So if we say limit exists, then it means right hand limit and left hand limit equal to each other. If we say limit does not exist, that means right hand side limit and left hand side limits are different. Okay. All right. So here from example 5, there are 3 figures given. So from the 3 figures, what should be the conclusion, or what type of conclusion can we draw from the given figures? Let me ask you one by one. In the first figure, does limit exist at x equal to a?
No.
Why? You have to mention the reason behind your answer.
So if we approach A from the left-hand side, it ends at 1. And if we approach A from the right-hand side, it ends at 3. So there should be no limiting value at x equal to A.
Yeah, because the limiting values are different. The right hand limiting value is 3 and the left hand limiting value is 1. Since the limiting values are different, therefore limit does not exist at x equal to a. Now tell me, what is the function value of at x equal to a?
Two.
Exactly. So it has a function value which differs from the limiting value. Therefore, the function is discontinuous. Okay? Because in the next chapter, we will learn about the continuous function, and in that chapter, we will see there are 3 conditions for a function to become continuous, and one of them is function value should be equal to limiting value. Here, limiting values are different as well as limiting value and the function value are also different. So function is discontinuous at x equal to a. What about the middle figure, the second figure? Can you make a conclusion from the second figure?
So from the second figure, I can tell that there is no limiting value, but the function value at a is 1.
The function value at x equal to a is 1, as well as the left hand limiting value is 1. But right hand limiting value is different, which is 3. Okay. And from the third figure, we say there is no function value at x equal to a, but there are two limiting values, either from left and right hand side, but they are different to each other. Therefore, the limiting value of the function is 1 for the left hand limit and 3 for the right hand limit. But still, there is no function value at x equal to a. Okay. All right, so move to the next example. From the first figure, what is your conclusion, or what type of conclusion can be drawn from the first figure? This is definitely a absolute value function curve. From the curve itself, we can see there is a breakpoint at x equal to a. So what is your conclusion from this figure?
There's no function value at x equal to a, but both of the limiting values are 2.
Exactly. So limit is existing, but function is not continuous. What about the next one? What about the next one? That means the middle part of the figure. You have to answer. Without answering, I cannot continue my online class, right? You have to respond from your end. This figure indicates that limit does exist at x equal to a, and function value is also existing at x equal to a, which is 3. Since the function value is not equal to the limiting value, therefore we conclude the function is not continuous at x equal to a. But in the final figure, the limiting values as well as the function value all are same, which is 2. Therefore, the function is continuous at x equal to a. Right?
Yes,
Next,
sir.
infinite limits. Whenever we utter infinite limits, that means the limiting value is either plus infinity or minus infinity. That means the function value is approaching towards either plus infinity or minus infinity. Look at the graph given below. This is the well-known elementary curve y equal to 1 over x. So if we approach x much more closer to 0, what is the function value if we approach from the left hand side of 0? What should be the function value? Or you can say the limiting value. What should be the limiting value if we approach from the left hand side to 0? Obviously, it is negative infinity, right?
Yes, sir.
At the same time, if we approach towards 0 from the right hand side, the function value is approaching towards plus infinity. Therefore, we say the limiting value is plus infinity. Now, the bottom line of this concept is if we observe limiting value as either plus infinity or minus infinity, we can conclude or we can say limit does not exist at that particular point. That means limiting value plus infinity or minus infinity does not indicate the existence of the limit. Do you understand? If we get some finite value, finite limiting value, only then we can say limit does exist. But if we observe or if we get any limiting value which is infinite, then that indicates limit does not exist. Okay, clear? So there are several examples supporting this concept. So you can go through the following figures. Next, we are moving to vertical asymptotes. Asymptotes have already been discussed in the primary lectures or in the prerequisite lectures. So here we'll talk about vertical asymptotes. So what does it mean? Vertical asymptote means a vertical line that gives a guideline for a curve. That means the curve will pass very closely to that vertical line, but it will never touch or intersect that line. Okay, so this is called vertical asymptotes. So here you can see there are 4 figures where the curve is passing through very closely to a vertical line, but still it does not intersect or touches that curve. So in every single cases, these vertical lines will be treated as vertical asymptotes. All right. So this is all about this preliminary chapter of limit. You can go through the chapters thoroughly and then move to the next chapter. That means next section, computing limits, how to compute limit of a function, how to deal with limiting problems, limiting value finding problems. So before entering the next section, we need to learn the theorem stated in 1.2.1. Here you can see there are 4 particular scenario or 4 particular situations where we are looking for the limiting value. The first one, limit of a constant function k if we approach x towards a. What should be the limiting value? That means if we consider a constant function and we are approaching x towards a particular value a, then the limiting value should be the constant function itself. Do you understand what I'm saying?
Yes, sir.
Which is confirmed by the first figure. The leftmost figure is confirming this part. And the next theorem or the next part of the theorem indicates if we take a function y equal to x and we are looking for its limiting value at x approaches to a, the limiting value is the constant already been discussed in the previous section. So for the case of C and D, we say limit does not exist. Since the limiting values are minus infinity and plus infinity respectively, that means limit does not exist in this case. Okay? Next theorem, 1.2.2. If we consider the limiting value of two separate functions separately, we are looking for the limiting value of the function f as we move towards a is L1, and the limiting value of the second function g as we move very close to a is L2. These are given values. Okay, so now our next target is to get the limiting value of the summation of the two given functions f and g. The summation of two functions and then applying limit gives us exactly the same value if we take the limits separately and add the limits. Okay, so দুইটা লিমিট সেপারেটলি বের করে অ্যাড করলে যা হবে, দুইটা ফাংশনকে অ্যাড করে লিমিটিং ভ্যালু বের করলেও একই জিনিসই হবে. So I'm again saying taking the individual limits and adding them together gives us exactly the same value if we first add the two functions and then find out its limit. Okay, A and B similar. A is for addition, B is for subtraction. C is for the product of the two functions. That means taking the limits separately and then make their product. In part D, if we take the limit of a quotient function, then we have to take limits separately and then take the ratio of the limits. But here you have an close observation, or you can say you have a limitation that L2 should not be equal to 0 because something divided by 0 is not permittable. And similarly, part E, this is easily understandable. Okay, taking the limit of the nth root function is same as taking limit and then make its nth root gives you the same value. All right. So based on the assumptions or based on the theorems we studied here, we can solve the subsequent examples or the following examples. We can start with example number 4. First of all, we can start with example 1, where you can see there are three functions f, g, and h. So according to the rule, first we will take the limits separately and then we will add or subtract the limiting values. The next part, you can see there are products of three functions. That means take the limiting value separately and make their product. Okay, that means example 4 is giving us the application of the theorem we studied earlier. Okay, the next concept is finding limits of a polynomial and rational functions as x approaches to a. That means you are asked to find the limit of a polynomial function about a particular point of x, which is x approaches to 5, and you are finding the limiting value of the polynomial x squared minus 4x plus 3. So here you can apply the same rule or the same concept of the theorem we studied earlier. But one thing you might notice that limiting value or the function value of a polynomial function is always same. The reason behind that is polynomial function is always continuous as well as always differentiable. That's why for a polynomial function, your limiting value and function value should be same all the time. Okay? Is that
Yes, sir.
clear? All right. So now we are moving to the next theorem. This theorem actually indicates the same thing what we studied right now. For any given polynomial, p of x, that means this is a polynomial function of x, and we are given any real number a. Now, if we calculate the limiting value of the polynomial as x approaches to a, should be same as taking the function value at x equal to a. That means just substitute the values of x by a, gives you exactly the same limiting value. Okay, since at the beginning we are considering p of x as a polynomial function. So once you make sure that your given function is a polynomial, then there is no point of looking for its limit. Just take the function value and that should be equal to its limiting value at that point. All right. So by using this theorem, you can directly calculate the limiting value of a polynomial. Okay, so move to the next problem. Just look at the given problem. X approaches to 1. You are requested to find the limiting value of the polynomial x to the power 7 minus 2 to the 2x to the power 5 plus 1 to the power 35. Okay, so first consider x to the power 7 minus 2x to the power 5 plus 1 as a polynomial. As I mentioned, or as I said, the limiting value of this part should be equal to its function value. Just replace the x by 1, then you will get 0, and 0 to the power 35 is always 0. That means your limiting value should be 0. Okay. All right. So now moving to the next example, example number 7. The question is, find the limit of the quotient function 5x cubed plus 4 divided by x minus 3. So as you notice, this is the quotient function. That means we need to make the limiting problem in a separate way. That means you have to apply limit both in the numerator as well as in the denominator. In each case, you get two limiting values and then take the ratio will give you the final limiting value of the given function. But in problems like this, you have to make sure that the limiting value of the denominator should not be equal to 0. Okay, you have to make it sure. Otherwise, you cannot apply the rule here. All right, so summarizing the concept, let me conclude the section. Limit may be minus infinity from one side or limit may be plus infinity from the other. Actually indicate that limit does not exist. Limit may be plus infinity. It also indicates that limit does not exist. Limit may be minus infinity. It also indicates limit does not exist at that particular point. So based on these assumptions, we need to solve the following problems given in example 8. All right. So in example 8, there are 3 problems given: A, B, and C. So if you consider problem number A, what does it mean? What are the differences between the 3 problems? although the functions are same. Okay, in all three cases, the functions are same, but still, why we set three different problems? Can someone elaborate the reason? কেউ কি বলতে পারবে এক্সাম্পল 8 এ তিনটা যে পার্ট আছে, how they are different from each other, or you can say what are the differences between the three given problems?
So the first one, it says to find the limiting value from the right hand side to 4.
Yeah.
And in the second problem, it says to approach 4 from the left hand side. And in the third problem, it says to calculate the limiting value at x equal to 4.
All right, that means C is nothing but the combination of A and B. Am I right? To take the limit at x equal to A, we need to check both part A and part B to confirm part C. Okay, so we'll solve the problem one by one. Firstly, we'll start with A, problem number A, where we need to check the limit at x equal to 4 from the right hand side. So as you can say, we cannot substitute x by 4. Am I right? Can we substitute x by 4?
No, sir.
Because in the denominator, it becomes 0. So
Zero.
that means the function becomes infinite, or something divided by 0 is equal to infinity. Okay, but still we need to check whether it is becoming infinity in the negative direction or in the positive direction, because infinity has two directions. Either it can go downwards or it can move to upward direction, right? So we can at a glance confirm that the limiting value is either plus infinity or minus infinity, but we cannot say it with confidence that whether it's plus infinity or minus infinity. To justify the point, we need to check the sign of each of the factors related to this function. Okay, there are actually three factors in the given function. One factor is existing in the denominator, sorry, in the numerator part, which is 2 minus x. This is one factor. And in the denominator part, there are two factors. One is x minus 4, another one is x plus 2. So when we approach to x equal to 4 from the right hand side, that means we need to take the values of x little bit greater than 4. Do you understand?
Yes, sir.
Yes, sir.
So if I take something greater than 4, then a factor x minus 4 will hold a sign positive, right? For example, you take x equal to 4.00001. That means which is greater than 4. So the difference between that x value and 4 is obviously positive. Okay. So anything greater than 4 gives the factor x minus 4 a positive sign. Anything greater than 4 also give the factor x plus 2 positive sign. Do you understand what I'm saying?
Yes, sir.
So plus and plus gives you plus. Okay.
Yes, sir.
But if I substitute something greater than 4 in the numerator, what should be the sign of the factor 2 minus x? Is it negative or positive?
Negative.
Negative. So in the denominator, we are getting a plus sign, and in the numerator, we are getting a minus sign. So what should be the ratio of -1 and +1?
Minus.
Minus. That means the limiting value is infinity, but due to the sign, it should be minus infinity. Okay. Do you understand?
Yes, sir.
Now move to the next part. Move to the B part. Part B. If you take something less than 4, what should be the sign for the first factor in the denominator?
The sign will be plus. Positive.
Negative, and negative is positive, right? And here,
Negative.
negative. What about the ratio finally?
Negative.
Negative. So answer is infinity, but it should be negative infinity. Okay. So you can clearly understand the idea from here. You can see the one step-by-step formula has been discussed, and you can just check the sign from the real line. Okay. So sine of the function 2 minus x divided by sorry, divided by x minus 4 into x plus 2. First of all, you have to fix the points where we get 0 or plus infinity. This is called sign test. Okay.
Yes, sir.
Which value of x brings the function value 0?
2.
2. That's why we have to put a 2 in the real line. And what value of x, what values of x bring the function value infinity or undefined?
4.
Only 4?
And negative 2.
4 and negative 2. Very good. So first we need to identify the values where the function values become either undefined or 0. So there are 3 particular values of x where we get this type of scenarios. Okay. Next, since we have 3 particular values, so 3 particular values make the partition number 4. So there are 4 partitions. One is from the negative side of -2. Another partition is from -2 to +2. The third partition is from 2 to 4. And the final partition is from 4 to so if we move from the right hand side of 4, what should be the sign of the function?
Minus.
Minus, all through minus. So limiting value of the function as x approaches to plus infinity, sorry, x approaches to +4 is minus infinity. Do you understand?
Yes, sir.
The limiting
Yes,
value,
sir.
limiting value of the function as x approaches to 4 from the left side is plus. Do you understand?
Sir.
So this is plus infinity. Now you can ask me, how do I define this plus minus sign? To understand how it has been set, have you understood the mechanism, how the signs are put or how the signs are designed?
Please, sir, can you repeat?
Okay. For the first partition, which is actually from -infinity to -2, you can arbitrarily choose any of the function, any of the value of x, which lies in the domain -infinity to -2. You can arbitrarily pick one of the values of x, which lies in that domain. -infinity থেকে -2 এর মধ্যে যে কোনো একটা ভ্যালু তোমরা পিক করো যেটা তোমরা ওই ফাংশনে বসাতে চাও। Just pick a particular value which lies in that domain -infinity to -2.
Okay, sir.
What value would you like to take?
Can we take -3?
-1.
Minus. -1 is not located in that domain.
What about -3?
-3, okay. Just put a -3 here and check its sign using your calculator. তোমরা কি ক্যালকুলেটরে ফাংশন ভ্যালু চেক করতে পারো? Can you check the function value from your calculator?
Yes, sir.
Just copy the function as it is and then press the calc button. There is a button called calc. Calc stands for calculation. Okay, so just try it now. If you have your calculator, just copy the function 2 minus x divided by x minus 4 into x plus 2 and then press the calc button. Once you press the calc button, it will ask for the x value. It will ask to put an x value. Okay, can you confirm it right now? Can someone confirm this point?
Yes,
So
sir, it does.
yeah, you already checked. So once the calc button is pressed, it asks you to provide the x value, right? So put the value of x as -3. Just press -3 and your answer should be any value which is a positive value. Okay, is that clear?
Yes, sir.
So if you choose any value from this domain, your function value should be always with a positive sign. That's why plus signs have been put here. If you put x equal to -2, what would happen if you put x equal to -2? You will see math error. The calculator will reply math error if you put x equal to -2. Can you confirm it?
Yes, sir.
Therefore, on top of -2, there is nothing written. There is a void part in this region. Okay, that means we cannot look for a function value at x equal to -2. Now, if you move to the next subdomain, which is starting from -2 up to +2, if you arbitrarily choose one of the values in this domain, you will see the function value should always be negative. For example, what value would you like to take from -2 up to +2 for your checking purpose?
1.
Take
One.
-1.
-1, okay. So যে আগে ক্যালকুলেটরে ভ্যালুটা প্রেস করেছিলে এবার ক্যালকে গিয়ে আবার -1 বসাও। Just press -1 in the function value.
Yes, sir, it's negative.
It's negative. That means whichever value you choose from this domain, your function value should be always with a negative sign. Do you understand?
Sir.
That's why negative signs have been put in between this domain. Okay. And now, if I directly put x equal to 2, what should be the function value? If I put x equal to 0, that's why on top of 2, a 0 has been placed. Okay, clear? Now, move to the next subdomain starting from 2 up to 4. So for this subdomain, whichever value would you like to take for x?
0.
Okay, now press the calc button again and replace the value as x equal to 3. What is your function value now?
Sir, it's
If
positive.
it's positive. Yeah, that should be the thing. So any value chosen from the domain 2 to 4, your function value should always be positive. Okay. Now, if you replace x equal to 4, what would happen?
Sir, undefined.
Undefined or math error. That's why on top of 4, there is a void mark. No sign is given here. Okay. And the remaining part is similar. For the subdomain 4 up to plus infinity, you can pick any of the x values and substitute the value in the function. You will get your function value should always be negative. That's why negative signs are given here. Okay. Very simple, very easy concept. Just you need to understand the theme. Once you understand the theme, your calculation procedures will be much more easier. All right, now check the limits given in example 9. Check one by one. I'm giving you 5 minutes to check the limiting values. If you face any problem, you can ask me. Okay. Take 5 minutes to solve the 3 problems given here in example 9. Is that clear?
Yes, sir.
Okay, great. So using the sign test, you can solve problems like rational function limit finding or any function in the form of P by Q. Okay. In every time or in every case, you can apply the concept mentioned here. Okay. Mentioned by the sign test. You can solve problems like P by Q using your sign test. All right. this is another theorem. Just you don't need to memorize the theorem. You just need to understand the theme of the theorem, okay? Because you need to apply the concept. You don't need to remember the statement. You don't need to memorize the statement. Just use the fruit of the theorem. In this theorem, a function is given, fx is a function of x, which is a rational function, since this is a p by q form function, px by qx. Now, for any real number a, if the function value at a, that means q of a is not equal to 0, then limiting value of the function f is same as the function value at x equal to a. Okay, but if q of a is 0, then we say function or the limiting value of the function does not exist as x approaches to a. That means while dealing with rational function, every time you need to confirm that the denominator function should not be 0 at that particular point of x. So once you see q of x becomes 0 if you substitute x by a, then directly you can write the function is not existing, or the limit is not existing for the function f at the point x equal to a, or indirectly you can say the limiting value of the function f does not exist as x approaches to a. Okay, so based on this theorem, you can solve example 10. Example 10 is an example where we directly applied the concept of the theorem 1.2.4. So I'm giving it as your homework. So you will solve the problem. Example 10. This is your homework. Very simple. All right. Now I'm moving to example 11. This is very important type of problem for this chapter. Finding the limiting value for a function which is a piecewisely defined function. That means finding limit of a piecewise defined function. In a word, we can say finding limits of a piecewisely defined function. All right. So in my earlier classes, I discussed piecewise defined function. Am I right? Have I discussed?
Yes, sir.
Okay, so you have the idea how to deal with piecewise defined function. So how many splitting or how many pieces are there in the domain, in entire domain? How many subdomains are there? How many? Three. Very good. The first subdomain is from -infinity up to -2 exclusive. The second subdomain is -2 up to +3 inclusive. And the third subdomain is 3 to plus infinity, right? And if you find the limit of the function fx as x approaches to -2. So when we say finding limit as x approaches to -2, we need to split the problem into two parts. That means we have to check the limit from right hand side as well as from left hand side when we approach towards -2. বুঝতে পেরেছো আমি কি বলেছি?
Yes, sir.
Okay, come again.
Whenever you need to find the limiting value of the function as x approaches to -2, that indicates you need to find the limiting values from both directions of -2. Okay, so here we calculate the left hand limit as x approaches to -2. This is called the left hand limit, right? That means -2 তে আমরা যাব from the left hand direction. So whenever we move to -2 from the left hand direction, which function value should we use? এখানে তিনটা ফাংশন ভ্যালু আছে, তিনটা সাবডোমেইনের জন্য for three different subdomains there are three different function values. So whenever we move to -2 from negative side, which function value should we use?
1 divided by x plus 2.
Exactly, 1 divided by x plus 2. So if we put x equal to -2, what does it give? -infinity. Just using the sign test, we see this is -infinity. Okay, so now if we take the right hand limit, which function value should we use now? The middle one, right? X square minus 5. So this is a polynomial function. So according to the theorem, whenever we deal with polynomial function, then the limiting value should be equal to the function value. So we can easily replace the value of x by -2 and then calculate. So the limiting value is now -1. That means left hand limit is -infinity and right hand limit is -1. That means limit does not exist as x approaches to -2. Okay, is that clear?
Yes, sir.
And for the remaining two parts, apply the same concept. Okay,
Yes, sir.
a textbook gives you the algebraic techniques to calculate the domain, calculate the limit from different subdomains. But as I said, from now on, we'll be focusing more on the graphs. So if you sketch the graph properly, if you can sketch the graph properly, if you sketch the piecewise function properly, then your answer is very much easier from the graph. You can find out your answer from the graph directly. Now tell me from the graph, at -2, does limit exist? From the graph, answer
No,
your
sir.
question.
No, sir.
Because if we move to -2 from the left hand side, the limiting value is -infinity. If we move to -2 from right hand side, the function value or the limiting value is -1, which are quite different. But in the second part, if we find out the limit of the function as x approaches to 0, what should be the limiting value from the graph if we move to 0 from both directions?
-5.
-5. So in both directions, it is giving you the same limiting value. That means limit does exist as x approaches to 0. Okay. For the third part, for the solution of part C, if we take the limit, right hand limit or the left hand limit as x approaches to 3, what should be the function we need to follow for that? Which function should we use to calculate the right hand limit and the left hand limit as x approaches to 3? This part, the first part is indicating the left hand limit as x approaches to 3. Is that clear to all of you?
Yes, sir.
So whenever we move to 3 from the left hand side, we need to follow the parabolic function, right? Or the function x squared minus 5 should be used to calculate the limit. Do you understand?
Yes, sir.
And the limiting value is 4. But if you move to 3 from the right hand direction, which function value should you use? Because whenever you are moving to 3 from the right hand side, you are actually moving through the straight line. Not the straight line, actually it should be the square root graph of x plus 13. That means you are moving through this line, okay? So whenever you take the right hand limit as x approaches to 3, you should consider the function square root of x plus 13. That means you need to substitute the value of x by 3. Then you take 3 plus 13, which is root over 16, means plus 4. So in this case, the right hand limit and left hand limits are same. Therefore, we say limit does exist as x approaches to 3. Do you understand? So this is the most important type of problem from this chapter, calculating limits of a piecewise defined function. If you understand this concept properly, you can solve any problems from this chapter. So the whole exercise is given for you to practice. Try to practice each of the problems one by one. And if you face any difficulties, any problem, you can ask me in my next class, next offline class. Okay? So for the time being, I'm closing the session. Thank you so much for your cooperation and attention throughout this online class. Hope to see you again in next week. So for this weekend, your homework is to solve the exercise problems in exercise set 1.1 and 1.2. Okay. So after completing this chapter, in our next class, we'll be discussing continuity and differentiability and their related problems. Okay.
Yes, sir.
Any question or any observation from your
Yes,
end?
sir.
If you have any particular questions or any particular concern, you can raise your concern or you can ask me. Otherwise, I'll close the session.
Sir, Hardanton's book often contains many questions regarding graphs. So do you need to sketch the graphs too, or do you just do the algebra?
Well, very good question indeed. There is no fixed rule. If you sketch the graph properly, it helps you finding your answers more correctly or accurately. Okay. So I always encourage my students to sketch graphs, whether it's mentioned or not, whether it is mandatory or not. If you stick to your graphs, you don't need to go for detailed calculation. From the graph itself, you can answer your question directly. I'll give you full marks. If you properly sketch the graph and if you answer your question from the graph, you will get full marks. But for those who are not good at sketching curves or not confident enough to sketch curve, they can rely on algebraic techniques. If you rely both on algebraic technique as well as graphical technique, it's fine. Okay.
Okay,
But
thank you, sir.
my recommendation is to go for the curve sketching because it will help you finding your answer more accurately. Okay.
Okay, sir.
So thank you so much. Have a nice weekend. See you.
Assalamualaikum, sir.
Walaikum assalam.
Sir, what about the attendance?
Oh, I am giving attendance to all of you
Thank you, sir.
because I see most of you have joined to this class. So
Yes, thank you, sir.
Thank
Yeah.
you, sir.
Sir, but I don't have Friday after now.
Assalamualaikum, sir.
sir.